Now.
1, 2, here we go.
Okay, I think we're good to go. Hello, everyone, and thank you for joining us once again. Thank you for joining the whyr webinar series. Today, we are joined by Amal Saadallah, who's joining us from Dortmund in Germany. And thanks for joining us. I've been meeting. I'm hoping to have you join us for quite a while, and finally delighted you're finally here. I'm joined by my colleague Laisa Cavallo, who's the producer, our backstage supremo.
Hello,
And
everyone.
so, what we're going to do here is, do we have some slides there? We're just to sort of go through some quick announcements. Essentially, the
Yes.
first thing we do is we like to thank our sponsors, Jumping Rivers. Jumping Rivers are a training and consultancy agency based in Newcastle in the United Kingdom, and they have been great supporters of the R community for the last while. They've been supporting our user groups and the likes of Saturday's events and so on. And so they are. I'm a little bit ahead of the slides, am I? Anyway, so jumpingrivers.co.uk, and I am a little bit ahead of the slides. Let's slow down here a little bit. So yeah, thank you for joining us. And if you're not a subscriber, please subscribe and please keep a lookout on our videos. And feel free to look at our past catalog there. Now, there we go. Jumping Rivers. That's Jumping Rivers. So that they are the supporters that we have, and we're delighted for their ongoing support. And the little robot there, jumping_UK, is if you follow me on Twitter. So today we're joined by Amal Saadallah, who's going to be talking about automating time series forecasting with R. And as I said before, I've been delighted to have her join us today, and that I've been meaning to have Amal on the show, on the series, for quite a while. And I believe that we have a thing about next week's webinar. We're going to have some more webinars in March. We're going to be doing 2 a week. The next one is David Gohel, and he is joining us next week. And he's going to be doing 2 webinars back to back on the officer and flex table packages. It was really interesting. So without further ado, I'll hand over to Amal there and let you get set up. I'll let you share your screen. So Amal Saadallah, thanks for joining us. You're joining us from, I'll let you introduce yourself, really. We always let you introduce yourself. So,
yeah, thank you.
But I tell you what, I'll just let you take it away there, and you can share your screen, and I will leave you to it.
Okay, thanks. So good afternoon, good evening, everybody. Anyhow, now it's 8 p.m. So today my talk is going to be about how to automate time series forecasting using R, and just maybe some few words about myself. So I work as a research assistant in the artificial intelligence group of the Technical University of Dortmund under the supervision of Professor Katarina Morik. I'm also a member of the Collaborative Research Center, SFB 876, and particularly I work within the subproject B3 data mining on sensor data of automated processes.
Hello. I'm really sorry to interrupt you. I'm really sorry, but we cannot see your slides.
Oh, sorry.
No, you're fine. Imagine that. That's why we're here. Oh, you're doing great, by the way.
Thanks. Yeah, still, I hope that the audio quality is nice. Yeah, is it fine like this?
Yes, now we can see everything. Wonderful. Thank you.
So, okay, just sorry about the delay in sharing the screen. So as I told you, that I'm a research assistant in the artificial intelligence group of TU Dortmund. I'm part of the Collaborative Research Center. I work on data mining on sensor data of automated processes. And you may visit our project webpage to get a wider idea about our research activities. With regard to the research topics that I'm currently investigating, I'm looking more deeply into sensor data mining, time series analysis, ensemble methods. Currently also we are working with industry 4.0 related application for quality prediction in real-time manufacturing systems. That's why we look to data mining on process simulation. We integrate also process simulation together with sensor data for perspective and predictive analytics. And we aim also at using generative modeling to replace process simulation to be real-time capable. With regards to developing my own learning frameworks, I use mainly R. And before to start with the talk, I would like to give you an overview about the outline I will be following today. So our topic today is time series forecasting. So some advantages, the challenges that are imposed by such a task. And afterwards, I would like to give an overview about ensemble learning to, again, in the context of time series forecasting. And afterwards, I will give you details about some developed frameworks within the context of automated construction of ensemble methods for time series forecasting we have been developing over the last 2 years, and how you can run our frameworks in R and produce also your own results. In the end, maybe some few words about another application that we have been developing. It's more in the it's, let's say, application focused on taxi passenger, short-term taxi passenger forecasting. And then I would like to share with you the results also we achieved within this project. So to start, for time series forecasting involves learning models that are able to observe historical time series observation, learn from this observation to predict uncommon future time series data points. And for time series forecasting have been proven to be a very important task for a wide variety of fields whenever integrating it in some decision-making processes. For example, within stock market price movement prediction, weather indices, traffic flow, for traffic management in the context of smart cities, in some medical application within, for example, daily heart rate variability forecasting, etc. However, the dynamic behavior of some time series data itself make it subject to uncertainty, which makes forecasting as a task challenging itself. While looking to the machine learning literature, we may see that many solutions have been proposed to solve such tasks, including time series forecasting methods like I would mention, for example, the autoregressive moving average ARMA family of models, regression models, because whenever you are looking to a time series, you can also transform it to a kind of a regression task that can be a regression task, and afterwards you are free to apply a wide variety of regression models. However, within the experience also, it has been proven that none of these machine learning methods that are currently developed is universally valid for every forecasting task. So you cannot select one machine learning model and you say, oh, this is my gold model for every forecasting task. Even while looking also to the same forecasting task, machine learning models have different behavior along different time intervals due to the dynamic behavior of the data itself, which make also the use of a single model itself not valid for every time period. And here I want to show you an example showing the real versus the predicted values of the scarlet fever incidence in mainland China. And here you may see that we have fitted different models, including regression, exponential smoothing, ARIMA, support vector regression, etc. If you look to this part of the data, you may see that we are perfectly aligning to the true values, and it's kind of stationary behavior till some given periods. However, while advancing in the time, you may see that our time series is starting to have non-stationary behavior, but also the performance of our predictive models start to change, and you have some models that are assumed in the past to be valid for producing your prediction who are not valid anymore for use. And here the user or machine learning experts have to act and to set up rules on how to select the right model in the right time instant. And here one can think that the combination of many models can be a way so that you decide on how to combine many models together. And here the combination is a wider sense of also selection, because within the combination also you can set up rules for selecting one single model for each time instant, instead also of combining them. That's why the wider sense, I would say, is to combine them together and this is handled in machine learning using ensemble methods. And as you may see, due to this change in behavior in time series data, ensemble appear as a very attractive solution. And when we evoke ensemble methods, there are three main stages that one should go through in order to construct an ensemble method. The first one starts with the base model generation. So whenever we do have a given learning task, let's look even to the general supervised learning setting task, where you have a set of explanatory variable given a target variable that you want to model by this set of explanatory variables. Then you start by devising a set of hypotheses, can be, for example, n hypotheses, resulting in n different machine learning models. And afterwards, you may also look to your task, and then based on some performance analysis or some domain knowledge, you decide for a set of hypotheses or a set of models that you want to keep out of these n models. Afterwards, each of the kept models will produce its own prediction, and then the third stage comes on how to combine them together, or on how to decide for a combination rule that works efficiently during time. And if we look to the formal presentation of the task, then we assume that we have a temporal sequence of value till time t, where x is like the particular value of the time series at a given time instance. Imagine that you have a pool of models for a wide variety of models, constructing a pool of regressors or forecasters that are trained to approximate an unknown function f or an unknown process that have generated our time series. And our goal within constructing ensemble is to combine all these sets of models together to output one single prediction that would approximate our unknown process or unknown function the best. And basically, if we look to a particular time instant in the future, the output of the ensemble is decided by a given function which learn a mapping from the m-dimensional output of the single models to one single output. If we look to the very particular way of combining, this can be done by a linear weighted convex combination of the outputs of the single models, so that the decision here is decided by minimizing the expected squared error of our ensemble with regard to the true value given the set of the historical observation, and of course with regards to set to keep in the convexity rule by setting up the weights to be positive and to sum up to 1. Here, as you can see, the weights are time dependent. However, in most of the work that are currently presented in the literature, these weights are usually set up as constant during the time, or just learned once and then kept the same during test time. However, as you have may seen, I mean, the behavior of the single models may change over time, and so on the performance. That's why also the right formulation of this weight assignment should be a function of the time. And if we look to the most existing popular approaches, they are mainly focusing about optimizing the last stage within the ensemble construction, and basically we can distinguish different types or different families of models, including simple averaging models relying on computing either average of all the output of the base models or a weighted average over the time, regret minimization based families of models. Some models also are relying on the paradigm of meta-learning, so that you learn another machine learning model that will learn this exact mapping between the single prediction and the output of the ensemble. And also some recent work have started to transform the paradigm of reinforcement learning to decide for the ensemble aggregation. And I will maybe explain you with more details later what's currently going on within this family of methods. But the existing solution or approaches, I would say, still suffer from many limitations, including that, as I mentioned it, they focus only on the last stage, which is the combination stage. And even when they decide for a rule, for example, using some meta-learning approach or any other rule, this rule either is kept static along the time, or it's adapted at each time instant or periodically. So the adaptation is made, let's say, in blind manner without taking into account the dynamics in the time series or the need to change the rule or not. Because this is also decided with relation to the time series itself, but also with relation to the performance of the base models. And here I want to show you another example which shows the real versus some predicted value of the SP500 from Yahoo Finance. And if we look in more details, you can see some areas in the data where our forecast do not, or our forecasted values do not align anymore to the true value of the time series data. And this can be explained by the time series data being itself subject to concept drift. And this is formally can be expressed by the fact that the conditional probability of observing a given value for the time series itself at a given time instant t, given all the historical observed records of the same time series, is different at each time instant, or you may find some time instant t in your time interval where there is a deviation between these two conditional probabilities. And here the question is how much we are really losing while relying on such inaccurate model, because forecasting is just a stage that is happening before some decision making, where you have to for example, change your policies, where you have to act or to set up your business policies, for example, based on some forecast values. And then, of course, relying on an accurate model, we rely on an accurate also decision making. And here the question that we want to solve is how we can build adaptive and dynamic ensemble methods in real time without also spending too much structural and empirical efforts, because also you do not want to keep either updating your models at each time instant or do some blind adaptation in periodic manner, because this will be also computational very expensive. And I will show you this also in the experiments. So before moving to our approaches to the problem, I want also to show you some of the existing state-of-the-art methods and some of the art packages that I personally find very interesting, and I use them also for comparison with our methods. The first one are just very simple one, the static ensemble, where just you take all the output of the single models and you combine them using a simple average. The second one is a sliding window ensemble, where you try or you compute the recent performance of your single base models, and then you decide for the weight of the ensemble in such a manner that you penalize the most inaccurate models within your group of your base models. And you can also do a time sliding window to compute this performance in a stepwise manner. One of the also, I would say, recent works, not that recent, but still I find them very competitive frameworks, the one that are based on regret minimization. And here you find a very interesting package called Opera, online prediction by expert aggregation. So here the rule, the idea behind it is to keep a fixed set of experts, and also you have a fixed aggregation rule that you decide. So either it's an exponentially weighted average or a fixed share approach, where you just select the best expert across the time, or you use only, for example, online gradient descent to optimize the linear weights, as I showed you in the previous formulation, or you use polynomially weighted averages. So you start by fixing an aggregation rule, you fix your set of experts or base models, and at each time instant you try to update, or you learn a way on how to update the parameters of your aggregation rule based on some regret minimization with regards to the error suffered from your fixed aggregation rule, and your fixed set of models. So basically, how you do this if you want to run this in R. You compute a matrix or a data frame that contains the base model's prediction that can be computed either on a training set or on a validation set, most importantly on a set where you can also observe your target time series sequence. So this is the target time series sequence that you want to predict. This is the matrix containing the base model's prediction. Here you decide for the aggregation rule, which can be exponentially weighted, some fixed share, or some polynomially weighted aggregation rule. You decide also for the loss type, and then you run you run this model in order to learn the right parameters for your aggregation rule, and afterwards you can deploy it at test time to combine your set of base models following the selected aggregation rule. There is also like one very old paradigm which relies on the simple application of meta-learning, or the so-called stacking. Then you learn a combination of your base models using a meta-learner, and by that you design a metadata set that contains the prediction of the base models together with the target response variable or your target time series. You can add to this data a set of meta features that, for example, contain some information about the statistical properties of your time series, some also behavior indicator or performance indicators for your base models. And then you select a meta learner. I think nice way, also an easy way to do it in R, because you have the carrot package, and within carrot package you have more than 143 different regression models that you can easily tune their parameters. For example, if we opt for gradient boosting machine, then you decide on how to feed this. For example, use a cross validation. You decide for your own grid on how to set your hyperparameter. And again, if you want to run this meta learning strategy on how to combine your base model, so all what you have to input is your target time series sequence that you observe on a given training or a validation set. And the train meta here is the data frame that is composed of the target time series and then the base model's prediction. To this data set, as I said, you can add a wide variety also of devised meta features, and then you call your meta learner. Here we decide, for example, it's a gradient boosting machine, and then you tune it so that you learn a rule on how to combine your models. And of course, you can either update this at each time instance, so whenever you do have an upcoming time series observation, you update your training set or your validation set, and then you rerun and you learn a new combination for the following observation. You can also update this periodically, but also we will show you later. I will show you later on how to update this in an informed manner so that you align also with the performance of the base models and the quality of approximation to the true time series. One very recent work that also was devised in the context of dynamic ensemble learning. The first one called ADE, arbitrated dynamic ensemble, which is learned to combine forecasting using a meta-learning strategy that is devised towards specializing the base models across the time series. And then at test time, what you do is you weight you rank your models based on their degree of a competence on some input observation, which is already estimated by your meta-learning. The second framework is an advanced version of the slide and window-weighted ensemble, where you basically you combine your model based on their performance. And while computing this weighted average, you take into account two facts that you want to keep in your ensemble. The first one is heterogeneity, which boosts the diversity inside the ensemble whenever, for example, you select base models that are belonging to a different family of machine learning models. For example, you include ARIMA family of models, some support vector regression, some Gaussian processes, and the responsiveness is promoted by tracking the performance of the base models, the recent performance of the base models, and include them in the weighted formulation or in the weighted aggregation of the ensemble. So, for example, you assign weights that are inversely proportional to the error of the base model, so that you penalize more the models making more mistakes in the recent observations. And you may find the implementation of these two methods in the TS Ensembler R package. And I want to quickly show you on how really to run this, because it's a very nice framework, and also they do have I will show you how you will have also the option to update this in real time at test time. So what you start with is that you embed your time series into a regression data set. So basically, whenever you do have a time series, you have a sequence of observation that ordered in the time. And by embedding them, you just decide for each of the observation how many lagged value you want to use as a set of explanatory variables. So each observation in the time series will get as feature the 5 previous observation, and by this embedding you can apply to your time series any type of regression model. And here you can set up the parameters of your base models, and you can see that you can apply a wide variety of regression models by applying this time series embedding to your time series data. And then you decide for the parameters of your models. And here you have within this package a list of models that you basically should use. So you can select all the models in this list, or some models within this list. Once you set up the model, you call your method, and then here you have the target time series data, the training data, which contains, as I told you, this embedding of the time series data, and then you specify the list of models that you want to use. Here, the size of the validation window on which you run your meta learner. The value of omega decides the percentage of the base models that you want to keep in your ensemble. For example, if you have 30 models, so just you keep only 15, the top best performing 15, and many other parameters that, for example, select the best here is set up to false, because if you set this value to true, then you will only select only one model. And then this is the type of the meta learning model that you use to predict the performance of the base models. Here is set up to random forest, and within this part, basically, you can compute your prediction, and then you can decide for a given time interval length on which you want to update your method. So it's 3 upcoming time series values. You can update your AGE model, and you update your base model by retraining them. You update your combination rule, and you update the weights that you will assign to your ensemble. For the second method, also you can I show you one example where you can only specify a certain type of model. Here is a support vector regression. So we just varied the parameter of the model, and then we called the DETS ensemble method to combine them together and to produce the prediction. Here, an example of some evaluation using the data set that that is already contained within this package. So it's a time series of water consumption data set. You can see some variance in the performance, which can be explained, for example, by of course the model being built on 2 different paradigms, but also some of the second method is only relying on using support vector regression. However, the first method, the AGE method, is using a wider variety of regression models. Now I would like to show what we have devised in the context of the dynamic ensemble learning. As I showed you before, like our time series can be subject to changes, to concept drifts, to non-stationary behavior. And of course, we should we should, I mean, keep in tracking these changes within the time series. So that if we want to construct any machine learning model or any ensemble framework that contains a combination of many machine learning models, it should answer to a set of requirements, including being suited to dynamic online environments, being adaptive to different construction level whenever we treat the ensemble part. It should be also adaptive to the deviation in the base model's performance, but also to the ensemble performance itself, because the deviation of the base models may change over time, but also your way on how to combine them may become also inaccurate over time. This adaptation should be done in an informed manner based on the changes that are really occurring, instead of doing it in a blind manner by either keeping it static or changing it at every time instant, which is very computationally expensive, or deciding for a period where you do all this retraining and change all these combination rules. And also you should keep a certain degree of flexibility and easiness even for non-machine learning experts. And basically, so what we have done, so we tried to build an adaptive ensemble methods that didn't also focus only on the combination stage, but also on the pruning stage, on how to select the base models that should be appear in your ensemble in the end. It has also performed a kind of a meta learning in the sense that it clustered these methods according to their similarity, so that in the end you construct an ensemble which contains a certain degree of diversity, which is a required property while constructing ensembles, because it contributes to reducing the variance type error of the ensemble. And also we use different combination rule, including using sliding window averages, stacking, etc. And here I want to show you the different components of our framework. So our framework focuses first on pruning, on select the base models that should take part in your ensemble, using top base models selection based on their relative performance, but also by clustering them into clusters, and then select only the representative of this cluster to take part in the final ensemble, and then combine them either using sliding window average in this example, or some stacking, or some meta learner. And the adaptation of this whole framework is based on drift detection in the relative performance of the base models with regards to the target time series to the target time series values. And basically within the first stage, we start with computing the drift-based models pre-selection by just getting the most recent windowed time windowed observation over user-defined time interval. And then within this interval, you compute the prediction of your base models, and then you store them. And of course, you compare, you store your true observed values of the time series itself, and then you compute a similarity using the Persian correlation between this sequence of values for each base model and the target time series, and this will result in kind of a correlation scores matrix between the base models and your target time series, and you keep tracking the deviation in the observed minimal correlation between your base models and the minimum value that you record at each time instant. And this deviation between the recorded the first observed minimal value in the recorded correlation and the current observed one should stay within a given bound, which is decided in our methods using the Houghton bound. And here are standing for the range of the values. And W is the size of the validation set on which we observe or on which we compute the similarity between the target time series and the prediction of the base models. And eta is a user-defined hyperparameter because basically in the first formulation of the Houghton bound, this deviation in the mean should stay within this. Should stay within this boundary with the probability of 1 minus eta. And then for the second stage, we want to group the models that have similar behavior together, so that only one representative of these models is apparent in the final ensemble. That's why we compute, we cluster these models based on their prediction on this time window. And for the clustering, we opt for a maximum likelihood based clustering, because basically within this clustering type, we can decide for grouping the models based on the covariance value, which is finally what we are opting for, because we want to get with the similar models over a sequence of time series values together in one cluster. And then if you opt for distance-based clustering, this can be misleading. For example, if we decide for example, for a Euclidean distance-based clustering, then you may group clusters that have high covariance between their different prediction values in different clusters based on the on some distance measure, for example, based on the Euclidean distance. However, they have a high dependencies between their values, and they are explaining the same patterns within your time series. And this is not what we are aiming for. So we want models explaining the same patterns within the time series to be within the same cluster, so that one representative of this model take part in the final ensemble. And after basically deciding for which model to keep, then you decide for the combination rule. Here it can be simply the user can decide either for opting for a sliding window average or computing some stacking approach like I showed you before. The most important part here that the adaptation or the update of all the pruning stage and all the stages that come after is based on this drift detection in the dependencies between our base models and our target time series. And I want to show you an example of evaluation of our framework. Basically, the whole implementation, you can find it in my GitHub. But here I want to show you step by step on how you can run it also yourself and produce some results. So basically, within you start by calling all the packages that you need for our method, because also we use a wide variety of base models, including some time series forecasting methods and regression-based models. And one very interesting package here that I want to highlight is whyr.pl package, which is designed for robust model-based clustering, for the improper maximum likelihood-based clustering that I mentioned that we used in our clustering. And the cool thing about this package that you do not need to tune the parameter, because it does automatically the parameters tuning and decides for the number of clusters, and also removes the outlier within your observation. So for us, the observation are time series sequences. So whenever also there are some outlying prediction by some of the base models, they are removed automatically within this clustering approach. And as I told you, do not have to decide also for the hyperparameter of the method. Basically, if you look to the setup of functions that we have developed, so they are developed in order to perform or to build the whole block of our dynamic ensemble. But there are some functions that you can use in some any other work, because this data lag preparation, it transform your data set into a regression data set using this time series embedding, as I explained. This calcul ensemble computes the sliding window ensemble. So H is like the size of the window that you have that you want to consider in order to compute the recent performance of your base model. The period is the current period you are looking into. The list of prediction it's a list containing the prediction of all your base models. And this is like the real, so that the real target time series, so that you are able also to compute the previous performance of the base model in a sliding window manner and update this step by step. Train models, it contains a big list of models, but here you are not constrained with the given type of models. As I told you, once you perform this time series embedding to this list, you can add any type of models you wish. For us, we have like 30 models running there, but you can add this incrementally, and then also you can add any type of models of your choice. With predict models, it simply predict the type of it computes the prediction of your models. Here you can, as you can see, you find like the testing data that you can give to this method. However, it computes also the prediction step by step. So it deals with your test data as upcoming streaming data. For the drift top K models input, so basically it computes this the drift aware pruning of the base model. So it decides for the base models that should be taken into account whenever a drift detection was detected within your time series data. So this tells you if you need to update the list of your base models taking part in your ensemble computation or not, based on some triggered alarms. The R norm C, it computes the scaled version of the Persian correlation, so that you can compute the similarities easily between the sequence of two time series values. And in our context, it was used to compute the similarity between the base model's prediction and the target time series within the validation set. The bias variance decomposition, it performs the known bias variance decomposition between true target values and some predicted values. And this runs also the last one runs the Wilcoxon rank test to check for the statistical significance of the difference in performance between two sets of forecaster. For example, you have forecaster one output in the prediction given set of prediction, you have your target time series value, and you have a second forecaster. And here it's a window that you can decide on your own on how to stepwise compare the performance between the two set of forecasters. Here an example of so this the last call that before to set up everything is like the data preparation. It simply embed, as I told you, your time series data into a regression data set, and then you splits just the data into some train and test. And most importantly here, you do have a validation sliding window data set that moves while you are testing your framework online. So whenever you have an upcoming time series data, then this validation window is containing the 10 recent observed values before your upcoming time series point. And then this is like the value for computing the performance for the sliding window and ensemble. And basically just you decide for the validation length that will be updated afterwards within the model training and prediction. And basically you train your base models on your time series on the training set after removing the validation set, and you compute your prediction. This step is just to show you the different performance of the different base models. So we have 30 running base models, including so you have many families of machine learning models. So we just sometimes vary the parameters of the base models, and you can see that they have relatively different performance. And just to show you the performance of the base models. And here afterwards you have to decide for the number of the top models that you want to keep. For example, if you have 30 models, for example, you say I want to keep only 15 models, but this is a number that you can set arbitrarily, because the method will decide itself the number of top models that will appear in the end, because basically it does this adaptive pruning based on the drift detection, but also it clustered the models automatically and then select only cluster representative amongst this model to take part in the ensemble. So you can put this, I don't know, as 15 here, but in the end you will have only some 5 models appearing in your final ensemble, and this is automatically decided by our method. So this function compute the top k performing models, so the top 15 performing models, and then it calls the drift based function I told you about in the set of functions, so that it checks for the occurrence of drift, and if there is a drift, it trigger an alarm here, and based on this alarm, it updates the selection of the base model. And here I want to show you an example of the evaluation, just to say, I mean, this is done in a stepwise manner, even though I showed you here the computation for the whole test set, but this is done step by step, assuming that, or just imitating the fact that you are working on a streaming environment. So if you look to these first 3 time series data points, we don't have any changes in the relative performance of the base model, so there is no need to change them, and there is no need also to change your combination rule. Here it tells you that there is an alarm. So an alarm is triggered, there is a drift in the relative performance of your base models compared to your target time series on the validation set that is kept sliding also. And if you see here the list of the selected model, how it changed between this third value in your time series in index and the fourth index in the time, and you can see that maybe the first top performing model didn't change, but the remaining models also change, and we have a new apparent model like Gaussian processes with Laplacian kernel. We have also new multi-layer perceptron with the 3 hidden layers, etc. So, I mean, you can see clearly that the list of your top performing model also has changed. I would like also to maybe move faster now. And afterwards, you compute your clustering. And based on your clustering, so the cluster also is updated based on the detected drifts on your time series data. And after performing the clustering, you can combine, the method selects for you the cluster representative to take part in your final ensemble members, and they are combined together using some weighted average or sliding window weighted average, to be more specific. You can also use a stacking here. If you call this compute cluster top, this is the type of the cluster that we are using, and the stacking approach, and the stack is standard that you should use stacking instead of simply using an average. So the code is in the GitHub is commented, so we will find all the instruction on which method is doing what. And for the stacking, we have also 12 stacking approaches running. And here, simply, I selected the third one because it's based on ridge regression, which is known to be good performing in deciding for the weighted linear combination of the base model together with L1 and L2 regularization. So that also some of the base model are suppressed automatically by setting up some weights to very small values. But you have also wide varieties of stacking approaches here, including gradient boosting machine, random forest, etc. And with also the clustering, if you go to the code and to the GitHub repository, you will find also clustering using different other methods which we use for comparison. As I explained you, I mean, the appropriate one is using the improper maximum likelihood based clustering, because it estimates implicitly the covariance, which is desired to group base models based on their timely dependence structure together in one cluster. However, you will find some implementation using k-means, dynamic time warping clustering, and many variants of this model clustering. So when it's kept static along the test time, when there is some blind adaptation periodically, where it is also updated at each time instant. It's computationally way slower, of course, but just, I mean, if you are curious to see how different clustering is behaving with different update strategy, and the informed one, which is our method following concept drift detection. And here, just to quickly show you the advantage of such approach in comparison with many state-of-the-art methods. This is the support vector regression Laplacian, which is the base model, the single base model having the best performance. That's why I put it here. Random forest gradient boosting machine are known as a very classic ensemble technique, but also AGE, the package the method in the package TS Ensembler I showed you previously. That's Ensemble, also all these Opera set of methods, and including also some variant of our methods, including, for example, dynamic time warping clustering, performance clustering, selecting only the top models instead of doing the clustering. This is also the method using sliding window average, but you can see the best performing method, even comparing to all the remaining ones, was our method which computes the drift-aware top base models together with the clustering and combine them using a stacking approach. I think we are kind of running out of time, but I will go very, very quick just to tell you that we also transformed the paradigm of deep reinforcement learning for ensemble aggregation, in the sense that we consider high-dimensional action spaces as our set of weights that we want to attribute to the different ensemble members. The states are the observed time series values predicted by our ensemble, and we used an actor critic approach, which is fully developed in R also, to decide on how to weight or on how to decide for the combination of the ensemble. This work will be published this year in EEEE ICDE. And what we added as a new thing is some deep learning based methods that are also implemented in R using TensorFlow in R, Keras and TensorFlow in R, including the CNN based LSTM, the bidirectional LSTM, the convolutional LSTM, and those new family of models are also included with our set of base models. As I told you, I mean, in our reinforcement learning paradigm, the set of actions will be the weights that we will attribute to our ensemble baseline. The states are the observed predicted value by the ensemble, and the reward function is designed to be the rank of our ensemble with regards to all the competitors. And this have been proven to work quite well. And the cool thing here that we introduced some modification to the very popular actor critic learning framework by introducing a diversity in sampling the different rewards and states that we want to fit to our actor critic network. That's why even the computation in R was really very fast, and it was possible to run the whole framework in R, even though we had to run at each episode and at each iteration two multi-layer perceptrons that will perform as the actor and the critic in our reinforcement learning setting. Just to show you, and then the whole policy is employed in online, and by our improvement to this algorithm, we were able to, or we were successful in reducing the number of required episodes up to 100 compared to the state-of-the-art implementation, which require more than 300 episodes for conversions. And the number and the average time of running the policy to learn on how to set up the weight given a sequence of values of the time series predicted by the ensemble on a given validation set. Also, it tells you the next weights to set up in order to predict the upcoming values, and then it was 300 comparing to the random sampling and to the previous implementation of the method. And just to show you very quickly the performance of our reinforcement learning based method compared to all the remaining methods that I told you about, including our drift aware based framework, and the reinforcement learning based paradigm was also even better. And I want to show you also that you can using this drift aware adaptation of your ensemble framework, you are much faster compared to the best performance state of the art, which is AGE. And even comparing our reinforcement learning framework to this drift aware based to this drift aware based implementation, we are faster because we improved in the sampling. So just maybe I will not be able to go through the third framework. Maybe, I mean, I just included it in a kind of slides for maybe future discussion. But I want to tell you that the future the implementation of the reinforcement learning strategy will be made publicly very soon, because also we are improving this even further. I cannot tell you much more details because it's under review currently, but be sure that it will also be publicly available. I will not go through these parts, but maybe we keep it for future discussion or future work. But I want just maybe some few words. Whenever you are considering any machine learning task, including forecasting, when you add automation to it, you are faster and better, as you have seen in our results. In our future work, we want to fuse both frameworks together in an R package named O2 ETS. So stay tuned. It will be publicly available very soon, because we have one last work under review. And the current work direction that we are working on, and it's implemented in R, it's online deep learning model selection for time series forecasting, together with given some guarantees for explainability. And yeah, thank you for your attention. And of course, if you have some questions, some interesting ideas that you want to share with me, I'm also very curious, and you can reach me out using these addresses. Thank you.
Thank you very much. That's great. That was like, I did not know anything about that stuff at all. It's like there's so much rich material there to cover. So there's a few questions on the chat, and so first one is, have you investigated tidy models and stacks instead of Caret? That's our package stacks.
Sorry, maybe I did not get correctly the question. Is it about the Caret library?
Sorry, Caret R package. So it's about the R package tidy models. I have a feeling it's very new, so I think that's really the tidy models is a fairly new package. So that you've been doing this work for quite a while, haven't you? So
yeah, but yeah, also like some of the developed frameworks also are quite new, like from last year to this year, and
yeah,
some works are still under review currently. Yeah, but maybe I didn't get to write the name of the package, but of course, I mean, there is no gold solution, as I mentioned it in the beginning of my talk, and many interesting R packages. I presented the one that I really find very close to what we do currently, because they consider this dynamic ensemble construction within different stages.
Good stuff. Just a sort of hand, just if Laiz is there, could you change us to gallery view? Good stuff. So the next question is: have you checked out? Again, it's to do with new R packages. So I'm guessing that it is. Have you checked out the following R packages: Time TK, Model Time, and Model Time Ensemble framework?
Maybe currently not, as I told you, but yeah, maybe there's a lot of new writing packages. But as I told you, we considered mainly the one that uses meta learning based strategies, and the one that, I mean, on the theoretical part, we are starting from the same starting point. But of course, I mean, there are many solutions and many ways. As I told you, even there is wide variety of work starting from meta learning paradigms, the regret minimization based approaches, newly the reinforcement learning based approaches, and so on.
Yeah. Just actually a very interesting question there actually with regard to Kaggle competitions. Have you seen any Kaggle competitions that would sort of like provide a basis for exploring some of this material? I think that's a very good question actually.
Yeah, I'm also aware of this M4 forecasting time series data in Kaggle, which have been made very popular. And also, to be honest, while even providing some results and evaluation of the different frameworks, also reviewers start to ask why you didn't evaluate on this M4 competition for Kaggle, but this is also will be included as a part of our future work. But also the evaluation that I have mentioned at least includes wide variety of time series data from different fields. At least, I mean, we use at least 20 different fields for evaluation of our results.
Good stuff. A follow-up question there, actually. Just a quick, it's a short question, really. What about sparse data in the general context of the whole?
I mean, sparse in which context?
Yeah, it's a sort of tough question, actually.
Yeah,
it's something to think about maybe on going forward.
Yeah.
I've got just a question, actually. I just got one question there. Did you try to benchmark the ensemble method predictions against a Kaggle time series prediction competition models? Would like to see how such an auto approach fares versus manual Kagglers. So that's a Kaggle related competition again.
Yeah, but as I told you, also we think about, I mean, the quality of performance of the models, but also many of the steps were theoretically founded steps. So basically, when I opt, for example, for model clustering, it was made in favor of enhancing diversity in Ensemble. And if you look further to the machine learning literature, why, for example, one could ask why diversity is a required property, for example, for ensemble construction. Then you have to look to the ensemble error decomposition, which, for example, when you have a single machine learning model, it's known that you have to get trade-off between bias and variance. If you move to the ensemble level, then you have three components there: the bias, the variance, and the covariance. Or if we want to make it more general, the averaged error plus ambiguity. And this kind of tells you that the covariance aspect is, let's say, increasing the covariance part contributes to reducing the overall ensemble error. And that's why, for example, you construct your ensemble in favor of promoting diversity. And this is, for example, what we have done with regards to the clustering part. And if you look even to the top base model selection, it was done with relation to by computing temporal similarity between your prediction and your target value. Because in the end, you want to keep models that are explaining very well the expected observation in the future for your time series values. And those steps were kind of deeply studied before even like putting them in one running framework or block.
Good stuff. Just one last question from me, actually. We didn't get to cover it, but it's actually very interesting subject matter. Can you just give us a elevator pitch about the Bright project that you didn't get time to cover?
Yeah, maybe, yeah, the time I was short of time because many theoretical stuff.
Yeah, I know, but
some example of implementation of our recent works. But for the Bright, the problem there was we wanted to predict short-term taxi demand for a given city, let's say, even though we worked on very particular examples. So we have a spatial temporal distribution where at each given target stand in the city, we want to give an estimate for the short-term estimated value of taxi demand there. And what we have done, exactly similarly to this ensemble construction, we tried to monitor the dependencies between the different parts in the city or the different stands in the city. And by monitoring such dependencies, we built a drift-aware multivariate time forecasting model, so that also you get, so whenever you model the future demand at a given city, you take into account the most influencing parts in your city or stands in your city in this forecasting. Together also we developed a drift-aware ensemble framework that changes between that selects different methods at each step online, so that also it align to the target time series values, and this was tested also on a huge I would say test bed, including 3 large cities: Porto, Stockholm, Shanghai. We have GPS data, which was summed up to more than 19 millions of trips, and the data was collected in stream, discretized, and then we performed all this stage I told you about. So you can also find the detailed description of Bright methods in our EEE TKDE journal paper. Also, we got our method that we have developed. This method I told you we developed for Bright as patent within the U.S. Office of Patents. Also, Bright was amongst the top 5 winning solutions in the Data Science Awards. I think you were a member of.
That's correct. That's the Data Science DATSI Awards. That's correct. Yes. Yeah. Sorry, I forgot about that actually. Yeah, we're very impressive. That is the DATSI Awards, which are a European-wide data scientist awards, and I was a judge on that. And Amal was one of the finalists of a very strong field, and so there was all 5 of the, I think there was actually 6 finalists, because they were all very strong. We were only supposed to pick 5, but we ended up saying, listen, there's 6 here that are good. So I can't discuss more about that. It's sort of like, but yeah, it was just to suffice to say that everyone who was on that finalist list was very impressive. So so it's that's good stuff. We have a quick question here now. It's been a little bit of discussion in the chat about it, but we won't delay too long. Just actually any recommendations for books or learning about this stuff at the start? Somebody who's a career young data scientist, any tips on how to get started on this? Any good books you recommend, or just,
maybe the one book that I really like the most is the multivariate time series forecasting. August. I always forget the name. Sorry.
We can put it in the description afterwards.
Yeah, but it's a very very popular one. I can put it on the chat afterwards. But There are many books. Actually, there is one particular one. I forgot the name of the author. I'm very sorry because
Don't worry. Yeah, I get you. When you're on camera, all of a sudden your mind goes blank. You know, you
one
just can't even remember your own name.
is a multivariate time series analysis for with financial application and with examples in R on how.
Okay.
Yeah,
So that's a good one to look out for.
this is why I like the book.
Good stuff. We're going to sort of leave it there. Just to sort of quickly remark, actually, something I forgot to do at the start is to sort of say hello to all the R user groups who are joining us. I believe we have quite a few people from Barcelona joining us, quite a few people from the UK joining us, from Greece, and presumably all over Europe and Africa. And we're delighted to sort of be part, be part of. Be working with all of the other user groups to keep a very consistent program of events going on. I believe that Oslo, our user group, have an event coming up very soon. Barcelona are very active, and look out for all of those events. We will. That's it. So yeah, just one quick question. When we'll wrap it up. How is the whole COVID situation working out for you? How are you finding that? How's you finding it a challenge?
Do you mean particularly for our work, or?
Yeah, just how you yourself like.
I mean, myself, I have been in home office now since 1 year, so I didn't go to my office. In the beginning, it was a little bit difficult, of course, at least to keep things running the way they are used to be. But afterwards, I would say I got used to it, because currently we do research, so it's the very standard typical thing that you do every day, so papers, codes, review, and etc. But yeah, of course, I'm amongst the people waiting for normal life to get back.
Me too. We'll wrap it up there. Sorry, just two more I forgot about. Vienna R and Pazur Poznan. So hello to you. I am, just to sort of all of the R user groups together, and keeping the R community strong. And so we'll leave it there. Amal, thanks very much for joining us. And I dare say we're going to see you in another R meetup sooner rather than later. And that you'll be sharing more about your knowledge about this stuff, because there's so much interesting stuff there. I've never seen a talk like it before. Maybe I'm not going to enough talks, but like yours. But I think we'll leave it there. Thanks very much, folks. Again, thanks to our sponsors, Jumping Rivers. Thanks to Laiz, who's the producer tonight. Thanks, Amal, for joining us. And I think we'll leave it there. So that's it. Bye-bye.